Hello. Welcome. Hello. Hi. Hello. Hi. I'm going to start teaching now. All right, guys, quiet down. Hello. Welcome. I know some of you are entering your 4th straight hour of learning stuff, and I'm sorry. But on the other hand, it gets it all squished in together, so that's nice. It does explain why half of you didn't leave at the end of the last lecture. I was very confused because I had nothing more to tell you, but James did, so that was all fine. So these, for those of you who don't like waking up at 9 a.m., I'm Chris. Nice to meet you. I am the lecturer for 2921. So at this point, you've had the 3 lecture hours, and what this 4th seminar hour is going to be used for is mostly oriented around a series of computer worksheets. The computer worksheets are to allow us to kind of get a feel for how we can work with the kinds of structures and ideas that we've been learning the theory of, how we can kind of see them in action in a way that just drawing them on slides isn't going to be so useful. I notice a lot of you have your computers here, and that is excellent. The best thing you can do to make this more exciting than watching paint dry is to bring along your own computer and to work along with you. Otherwise, you're just watching me press enter 50 times. And like, fine, could be more boring, but there's better uses of time. So, you've got your laptop. What do you do with it? You go to this page here, which is through Student IT, and has a whole array of computer software that you can download for free. Treasure this when you're a student, because nothing is free once you leave, including all of these things. A lot of these are things that we use in mathematics all the time. Mathematica and MATLAB are both part of my research workflow, and many of these other things are as well. So here I have picked out Mathematica. Now, you click through, you can download it, you can get a student license, and you can press enter with me, and we can share that experience together. But, I mean, in actuality, you're now at the point of math where it's time to incorporate tools alongside with you. There is no masochistic joy in evaluating an integral that a computer can do. The joy of these tools is they do the hard stuff so that we can focus on the ideas and the things that matter. I'm not sure I've evaluated a hard integral, except for teaching, for some time. Just because, you know, you could do it. I'm sure there's a transformation that a HSC student could tell me, but I don't remember them. That's what this stuff is for, so I can think about very clever ideas about vector fields. Are you okay? Yeah. Cool. About vector fields. Once during my first ever time I was lecturing at Sydney, which was in that room there X years ago, let's not delve too deeply into that, a poor student walked all the way to the top and then dropped her metal water bottle that proceeded to clank down every single step of the theatre. And like, you try and talk through it. You don't want to embarrass the poor person, but there was absolutely nobody in the class was listening to me anymore. Yeah, it's fine. Don't worry about it. All right, so for those of you who have Mathematica and have gone into Canvas and pulled out the worksheet, it looks like this. Now, my assumption is that you don't know anything. If you know anything, you are already exceeding my expectations. These notebooks are designed with the intention of stepping you through how to use this software, and also how to use this software in your later mathematical life, so that Martin doesn't come to my office and complain that students can't find eigenvalues of a 5x5 matrix. Today's is a bit more introduction-y. Can I have a hands up? And it's totally okay. Hands up who has this open in front of them. Okay, not so many. That is absolutely fine. I am going to go through this. But, you know, in the coming weeks, you'll get more value out of doing this along with me, because I already know this stuff. Some of the worksheets are shorter than others. I will also carry some supplementary questions, which if I accidentally go too fast, I will do at the end so that you get a bit more value out of it. However, today we just have this. So, it's computer software. And the thing about computers is they are very powerful idiots, which means we need to talk to them very, very carefully. We need to make sure, and this is sort of explaining how to do that. So to execute a command in Mathematica, you press Shift-Enter. So what I did was just executed this first command, clear. What this does, if you have any programming experience, you know what variables are and how you can allocate quantities to variables. I've just wiped its memory. It now knows about as much as a first-year student. So what we're going to do is start to tell it things. So you can use Mathematica as a fancy calculator. Honestly, this is like 90% of what I do with it. You can do more sophisticated coding, and I may show you some of that later in the semester, but we're going to basically treat this as a calculator. So 2 plus 1 equals 3. I think you could all get that right, but it's a bit of a more powerful calculator than that. So there are two ways computational mathematics programs process computing, and that is through numbers and through symbols. For instance, if you ever use MATLAB, which you should at a later stage, it is numbers only. It can't do symbolic stuff very well. The power of Mathematica is it can do symbolic stuff very well. So for instance, if I want to say y equals x squared, then it does this. But what that means is from now on, anytime I type y, it knows that that means x squared. And if I want to do y plus 1, that will be, the output will be 1 plus x squared. If I want to do y plus 1 all squared, the output will be 1 plus x all squared. Okay, so Mathematica is, you can think of as a variable calculator. It understands how to do these calculations. I'm going to make that bigger. It's still a little small. It's going to be giant on my screen, but I want to make sure that you at the back can see what's going on. Okay. So if x has just been hanging around and I haven't told Mathematica that x is anything, then Mathematica knows to treat x as a variable. And you don't have to use simple things. You could say, you know, Chris squared is double the number of Chris's. Square, all right, fine, whatever. I was coming up with something on the spot and it didn't go well. All right, so your variables, it makes sense to use the kind of mathematical symbols that you use. If you want to use Greek letters, escape, and then alpha, and then escape will give you the Greek letter. So you can use Greek as well. There is something to be said for using letters that are symbols that are appropriate to the kind of math that you want to do. So it's not a bad idea. I say that as good practice. I'm going to tell you a lot of things that are good practice that if you ever look at any of my Mathematica worksheets are not there. So do what I say, never do what I do. All right, so assuming that x hasn't been assigned to a specific value beforehand, then y just stores an algebraic expression. And then we can treat y as if it's an algebraic expression and do stuff with that. For instance, as it says here, we can differentiate y. So I've assigned y. I've said, yep, y is x squared. So maybe I can't remember how to differentiate. It will do it for me. dy dx. Okay. And again, any variable works. If I, you know, let y equal Chris squared, and I differentiate y with respect to Chris, now I get 2 Chris. There we go. Brought it back. But like, as I said, keep things simple. Use the kinds of variables that tell you what you're doing, and everything will work. This is very nice. It differentiates y with respect to x. Mathematica has a lot of mathematics built into it. It knows how to do things. And we will see that later on as it uses a whole lot of interesting rules. It knows how to do, for instance, partial derivatives. We'll see that later. Okay, some technical stuff that nobody enjoys, but it has to be done. There are input cells and output cells. This is an input cell. This is an output cell. We put inputs in the input cells, and output cells tell us the output. In some ways, because this is synchronous entry and results, it's a little bit different to programming in a typical programming language. If you're familiar with Python or C or any of the other languages that it's good to have a handle on, this will feel a little bit different because you're doing stuff and getting synchronous results and feeding it back in. That is okay, but it sometimes takes some students some getting used to. All right. You can hide contents of output cells and all of those things. If you don't want the output to show up, you put a semicolon in the end and it suppresses it. You may ask, why do you want to suppress it? But this makes sense when you do things like assignments. I already know y is going to be x squared. I don't need to see what it is. So in general, if you want to keep your note code neat, show the things you're interested in, but you don't necessarily need to see every single line. Right. Now, that is nice if you want to do differentiation. Later we'll learn about integration, anything else you may have been taught. You can do matrices and linear algebra operations, but that is for a later week. Today we're focusing on functions, learning to use Mathematica. Okay. So I've mentioned that things can be numerical or they can be algebraic, and we can use those expressions as allocations. So if I press enter here, you'll notice I do three things at once. So I stacked a few commands here by pressing Shift Enter at the end of a command. And what I've done is I've said, all right, if you see the number n, that is now the number 1 in your brain. If you see the letter y, it's this quadratic expression here. And if you see the letter u or the letter v, they are both 0. There's no particular special reason to do them like this. It saves time. It's probably bad programming practice, if we're being honest, because you really should do individual variable declarations on individual lines, because it's all good now, but when you read it 3 minutes before the exam, you're not going to remember what you were doing, or when you're writing the research paper. And of course, it spits out what you've done just to remind you in case you weren't paying attention to your own code. So to execute a command, Shift Enter. This is very important. A lot of people, when they first use this, try and press Enter. It goes wrong, they panic, and then they decide they hate computers forever. Not unreasonable. Okay. So there are other ways to allocate variables, and the way in which you allocate a variable really depends on what you want to do with it. So, you know, this is now whenever I use y, it will be x squared plus 8x plus 2. Now, if I give x a value, that will flow through, and it will say, oh, well, it's this. But it gets a bit tricky, so we're going to learn a couple of very convenient kinds of alternative assignments to avoid any problems. The first is the replacement operator, and I have a preference to putting curly brackets around that for readability. So this says, hey, what happens if I just want to substitute something into an expression and see what it spits out? This is very important. We are often interested in the kinds of expressions that we do at particular points. Maybe we're interested in knowing the value of a surface at the point where we plan to put up a tangent plane. That's all stuff we can do here. So if I want to do x squared, and I want to say, well, what is that if x is 2, and I press the right keyboard, I get 4. All right. What if x is 2y? Oh, I've already allocated y as something. 2p. 4p squared. So basically, this just takes whatever you give it and puts it in here. Now, what it won't do is any kind of simplification. So, for instance, if I make this the square root of p, oh, it will. Okay, normally it won't unless it's very, very simple. Fortunately, it can just about understand what happens when you square a square root. We will learn later about things that it can't do. I was hoping it was slightly stupider than it was there. Okay, so we do our replacement operator, which is very, very useful. This one is less useful. I almost deleted this from the worksheet, but some people like it. I tend not to use it. So if I normally assign variables, if I let x be 2, and then I tell it that y is x squared, it goes, okay, well, I know what x is, so I'm going to dig and dig and dig, and x squared is 4. 2 squared. Okay, so what has happened there is it's evaluated the x squared straight away. If I change x, does y change? It does not. It made the decision of what y was at the point where I assigned y. The understanding when things happen is a recurring issue with code. Does anyone know C? More than I expected. So this is the difference between a variable and a pointer, right? Like that is what you're seeing here in Mathematica terms. And understanding that difference when I learned C for the first time almost killed me. Okay, so y still has the value 4. Changing x didn't change y. There was no flow-on effect. If we wanted to start define something that is more akin to a function, then we can use this. So I can say x is 2, and y is defined as x squared. Now this delayed assignment means that it won't actually evaluate that until the point that you use y, not the point where you define y. And that means that if I say x is equal to 3 and evaluate y, it will now accept that y is 9. If x is equal to Chris, if we're lucky, y is equal to Chris squared. Good. So it doesn't do anything. If I say it's equal to square root of p, it's equal to p. So it understands and does the operation only when it's called. There are really good reasons why you don't want to do this unless it's necessary, particularly once you get into more complicated expressions or code structures where you don't want to be repeatedly evaluating complex functions every time you call them. So probably nothing that you have to do in this subject will this ever make a difference, but it can be the difference between code running overnight and code running into the next millennium if you aren't careful. You all laugh, but that was one of... I exaggerate a lot for comic effect, and that was not one of them. You know, this is a thing that can happen. When you're running quite sophisticated mathematical algorithms, they can take incredibly long times. There's an entire field of... I'm starting to talk over people, which is not ideal. There's an entire field of mathematics, the study of numerical analysis, which is really about the study of how accurate you can get algorithms to be and how you can optimize them to make sure they terminate within the lifespan of the universe. Like, numerical analysis is heavy-duty mathematics. We don't want to bother with that sort of thing. Use delayed assignments, but if your computer starts to chug, that might be one of your problems. All right, so I've assigned a bunch of things. I've assigned x. It's square root of p. I'd like to get rid of this. I'd like it not to know what x is. Okay, that's fine, Chris. Maybe just set x to be x. That did not work. The way you need to do this is to just tell it to forget everything. Tell it to go on mid-semester break. And there are specific ways to clear stuff in Mathematica. And this one here, which you might remember from the very top of the document, is the most important one. So you can clear individual variables. If I just wanted to get rid of x and nothing else, I'd just say clear x, and it's happy. Yep?
So is clear a regex, or is it a regular expression? Like, is it x star and you get 10x?
You can absolutely use regex in that. Yeah, that's what's going on there. But I don't want to introduce those ideas, so I'm just going to give you this command. Yes, that is absolutely what you're seeing. This says clear everything. Now, Mathematica, if you say, how do I clear everything, will tell you something different. And that won't clear everything, because it won't clear all of the delayed assignments. This will wipe out everything. Don't remember it, just save it in a Mathematica worksheet, like what I do. And then every time you need to clear something, go remind yourself of the exact syntax and throw it in your code. You can also clear a set of individual variables if you're keeping stuff neat. Okay. You now basically know how to set up Mathematica and kind of as much of how Mathematica works as you need to know. Mathematica stores objects. Those objects can be all sorts of things. We're going to see a really weird example of this later. But for the most part, it's a symbolic algebra toolbox. We're going to do a lot of pretty gnarly calculations. And, you know, you might get calculations in an assignment or the like. You're at the point now where we kind of expect you to be using this for algebra-type calculations. We don't expect you to go and, by hand, find 6 eigenvalues, solve a sextic, which maybe you get lucky. You type it in this, you take your medicine. You should really treat this as something that is a tool you can use throughout the entirety of your mathematics studies. We use it professionally. You are training to be professionals, maybe mathematicians, maybe some kind of other quantitative discipline, and that means learning to use all the tools at your disposal. Mathematics is absolutely a life of the mind, but the tools here help you understand and process and visualize that and really, really complement what we're teaching you. Not everyone loves computers. They came here wanting to pen and paper their way through a degree, and you kind of can, but you're leaving skills on the table and you're not using your brain to the most efficiency, because if this takes some of the tedium off your plate, then that can help you explore the real ideas and the guts of what we're teaching you. I.e., computers are good, learn them. Also, half of you are going to be consultants at the end of this. Learn to program. All right. So, we want to use this as a calculator. Then we need to be able to do arithmetic. And hopefully they are exactly what you think they are. Brackets. I don't trust my first years to get the order of operations right, and I don't trust Mathematica either. Use brackets liberally to make sure that it is doing things in the order you want it to. Powers, multiplication, division, attraction, subtraction. I refuse to tell you what they are. I believe that you know what those are. It will follow the standard order of operations, but you might not. So tell it specifically the order you want to do things. And honestly, if you have big, complicated expressions, don't try and do them all in one line. One of the best things about having variables is you can do a chunk of the calculation here, see what that gives you, use that to do another chunk of the calculation, and you can kind of block your calculations down into informative chunks. Don't work out the whole gradient operator in one go. Work out the x derivative, work out the y derivative, work out the z derivative, and then stack them all together. That is an efficient way to do this stuff. Why are there two kinds of mathematical computation? Why do we worry about symbolic versus numerical? I mean, if I can do symbolic, surely I can always do numerical. And you're right, but numerical is infinitely faster than symbolic algebra. Symbolic algebra, a computer has to interpret the mathematical context of what is written. It has to look at all of its mathematical simplifications and attempt to apply them. It has to work through and it has to spit it out. If you tell something that it's a number, it just does the operations like your C, like your MATLAB, like when you type numbers into the Google search bar because you can't remember where the calculator is. That's how it does that sort of thing. And Mathematica wants to take advantage of that when possible. So numerical evaluations. I wasn't kidding when I said we write code that might run overnight versus the heat death of the universe. And in part, that's the difference between numerical evaluations and analytical evaluations of code. So if I tell Mathematica to tell me what the square root of 41 is, does anyone off the top of their head want to take a numerical guess as to what that number is? Ah, I love teaching advanced classes. Mathematica says it's the square root of 41. It's like, what do you want? That's the exact answer. And it's right, but it was hard to tell, but there was a noticeable gap between when I pressed enter and when it displayed it. Not a long one, but a noticeable one. However, if I type n, 6.4, and it's essentially instantaneous. The biggest code overhead is the amount of time it takes to print the numbers to the screen. The calculation is hard-coded into like the embedded circuits. Numerical code is faster. We will use that fact down the track for a code that would actually take quite a long time to evaluate. Also, if you're bad at estimating square roots, I would have said a bit more than 6, then this will get you a lot more accuracy. Now, maybe I want a bit more than 5 digits. Maybe I want 100,000 digits. All right, this is an advanced class, and I gotta ask, who thinks they knows the most digits of pi? There's always like 3 people who want to have a pi off after class. All right, all right. Okay, okay. Sorry? Good. Square. The correct answer is about the square root of 10, which is a weirdly useful approximation. However, Mathematica's got you covered. Also, did you notice that that was very quick? Numerics are fast. So you can use Mathematica for arbitrary precision coding, which is very, very helpful. I've done a lot of numerics where often I need to know accuracy up to 50 digits, and Mathematica has got you covered. Actually, that's a little tougher to do in MATLAB. It's one place where Mathematica will sort you out. So, we're grown-ups. We like algebra. Numbers are for physicists. I'm joking. Physicists non-dimensionalize everything to 1. Numbers are for engineers. Simplify. So we have algebraic expressions, and we want to try and get the most out of this, and Mathematica is very skilled at this. So I have this function here, and I'm just going to copy it out and evaluate it on its own. Mathematica's like, yeah, I know what that is. Oh, I redefined x. Clear x. Hey, look, clear works, so that's nice. So Mathematica spits out this. Now, you can probably guess that these 2 polynomials might have some common factors. Mathematica isn't smart enough to see this unless you instruct it to look for this. So if you simplify, what it's going to do... Why is that open? Who knows what that might say? If you simplify, it will cancel all of the common factors. It will say, oh, well, it turns out actually quite a lot of this cancels. Cross, 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 cross. Simplify actually does a lot of other things underneath the hood. Often when you're doing quite complicated expressions, it's not a stupid thing to do to simplify your answer, just in the vain hope that something nice might happen. I had at least one paper become infinitely better because I just chucked a nasty expression into Mathematica, hit simplify, something comically simple came out, and then I had to go work backwards and understand why that was. Turned out it was for a very clever reason that looked very impressive in the paper. I did not think of it. Mathematica thought of it, so it's still my authorship. Simplify, however, does have some limitations, and the most important one, and this little fact can really mess with you when you're using Mathematica, is Mathematica treats everything as a complex number. MATLAB is the same. Complex numbers are a very natural field for computation to work in, so it will often do that. So if I say, hey, simplify the square root of x squared, so we're doing the square root of p thing, except we're going the other way. And it doesn't know what to do. It's like, well, it's the square root of x squared. You know what you want. And the reason for that, of course, is because in the complex plane, the square root function is multi-valued. So when you interpret it as a complex function, as you will learn when you take Math 2923 and the complex analysis part, you will learn that multi-valued functions play really important roles in the complex plane. And actually, a lot of the time we use Mathematica, we're exploring this, so we need access to that. However, if we know a bit more, if we're, say, restricting ourselves to the reals, you can add restrictions to what you're attempting to simplify with. So first restriction is that x is positive, in which case I expect this thing to be x. The second thing is the restriction that x is real. Given that, I should expect the square root of x squared to be the absolute value of x. It picks out the principal branch of the complex function if you care about that sort of thing. And these simplifications give you the values we expect to see. Okay, there is a more powerful kind of simplify. So if I try and simplify this expression here, then it will say, hey, my dude, I think that's already simple enough. It doesn't want to do anything more. But I hope you remember that there is a simplification to this. So if I do full simplify, Mathematica will try everything it thinks is sensible. Full simplify, Mathematica will just try every trick it's got in its kit bag, like someone who doesn't know how to do question 4 of an exam. And it will spit out cos of x. Say you don't want to use full simplify, because that on a complicated expression can hang up your computer completely. And you're just like, man, I just wanted the exponentials to go away. Exp to trig of this expression. We'll do that. And possibly, you might imagine that it understands the other way. Oh, no, cos of x. I'll get this right. And it does. So Mathematica can do smaller things. Any command you think Mathematica should be able to do, it almost certainly has buried in its system somewhere, with a few frustrating exceptions, but that is just for me to complain about and not you to worry about. Okay. If you can simplify, then of course you can expand. Expand x plus 1 times x plus 1. 1 plus 2x plus x squared. It can use complex numbers. You'll notice that the complex constant is a capital I. Most inbuilt commands in Mathematica start with a capital, and this is no different. The same is true of pi. So if I instead wanted this to be that, pi, I would say x minus pi. And it knows what to do there. So you'll see there's not I squareds hanging around. It's just I. So complex numbers will appear later in the semester, and it's good to know how to tackle those. Okay, so say I wanted to go back and say, well, I want to kind of know what those common factors were. Mathematica can factor expressions for you as well. So let's factor the numerator. Factor. Spell it correctly, might be a good idea. Factor. Okay. So probably the things that cancelled were 1 plus x and 3 plus x, and if you did the denominator, that would work too. In fact, let's try something kind of clever. Factor the denominator. 1 plus x, 3 plus x. Mathematica has numerator and denominator built into it. Anything you think you might want to do. Oh, and how do you find out what the correct Mathematica command is? I'm going to show you the help, but mostly you just go to Google and Google what is the Mathematica command to do blank. Because 10,000 mathematicians have spent their lives documenting everything this software does. Okay. Expand, factor, apart and together. I can never remember these two commands. I have to look this up every single time. Apart gives you your partial fraction decomposition. Weirdly useful. Together undoes that. I've never used the command together in my life except right now. So, very useful, never useful. Sorry? You can use so many different commands to achieve this, including simplify. There is no good reason. I'm sure there's like one use case where this was exactly the right thing to do, so please don't come and yell at me when you run into that use case. Cancel. Cancel just says cancel any common factors. Again, just simplify. Cancel works too. Okay. However, what we've just been doing is algebra, and this is a subject on calculus, so let's do that. Mathematica can differentiate. It can do a whole lot of other things as well, including on multiple variables. So you can assign single variables. You can assign multiple variables as well. I could assign a function of x and y and start doing multivariable calculus. Maybe I'll do that at the end. So what I've done is I've defined f of x to be x cubed plus 3x squared plus 4, and I've differentiated it. Sorry? The underscore is telling it that this is a function. So this isn't a delayed assignment. More or less does similar things, but Mathematica treats it a little differently inside. So this is how you define a function. If I wanted to do f of Chris, then I would get 4 plus Chris squared plus Chris cubed. which is altogether too many Chris's. So, the function df of x calculates the first derivative of f with respect to x. It won't shock you to know that you can do this again and again. Fortunately, you don't even have to nest the functions. You can just keep telling it how many to do. If I want to know the derivative of f of x, the second derivative, I get that. And in fact, maybe I want to do 10. I don't want to do this. What I do is I say the derivative with respect to x 10 times, which will be 0. But like maybe I could do it 3 times, and I get 6. So this is useful. We will use this a lot as we take more and more vector derivatives. Honestly, you do this enough and you kind of get in the habit of using this notation for any time you need to take multiple derivatives. Okay. You can also use dashes. There's certain contexts where it's convenient, but we'll cover those when we get to differential equations. And wait, what did I define g as? Oh, yes, I defined g as the derivative. Good, good. So this is the second derivative. You get it. Mathematica can differentiate. It can also handle partial derivatives. So here I'm defining a function in multiple variables. Now we're starting to talk about things that we will use. So hx is the derivative of this multivariable function with respect to x, and you'll notice it even color coordinates it for you to let you know what you're differentiating with respect to. H of fy, so the derivative of h of fy, probably set x to be something somewhere. Okay, nope. One thing at a time. This is why you always do one line at a time. Probably. Did I set y to be something? Ah, okay. All right, now we're cooking. Whoa. Okay. Derivative of h with respect to x. Derivative of f of x. So I've also clearly set f to be something somewhere. There we go. The derivative of a general function f of x with respect to y. Okay, so it's taking the derivative of... Oh, no, it's just evaluating h of f of x. Sorry, I confused myself with all of my extra variable. I just should stick to the path. And hy is this. Now, I can even do things like differentiate h with respect to x and y. Differentiate h of xy with respect to x with respect to y. And I get that. I can differentiate h of f of x with respect to x and y. And what it'll do is it will start differentiating my arbitrary function. So here, it doesn't know what f is, but it knows that in the evaluation of that, it's f dashed. So Mathematica is quite sophisticated at this stuff. We can integrate as well. Both indefinite integrals, so I've set f to be 4 plus 3x squared plus 3. Integrate it. You can all do that. And you can do definite integrals. And it evaluates it to an exact number. If I just need the numerical value, which is common for integrals, n integrate will do the job there. Integrate, n integrate. Okay, Mathematica has a very good help function. If you sit on a line and you wonder, what does integrate mean? Then you press F1. Press F1 on my computer. And it will open up on my other screen. And it will tell you. Mathematica tries to be helpful. It is often misguided, but it does its best. All right. Now, all of that is just being a fancy calculator, and that is nice. But I've often said that one of the most important things you can do is visualize stuff. And to visualize stuff, you've got to plot stuff. The command is not that complicated. If I want to plot x squared between minus 3 and 3, I type plot x squared between minus 3 and 3. And I get that. And it's great, and it's a quadratic, and it does it right. Now, what it has done here is automatically selected the y range to take in most of the function. That is what Mathematica will typically do, but sometimes that's annoying. So, for instance, if I wanted to plot x squared plus 2, it will do the same thing, and it will look identical, but we know there is a difference. This thing passes through 0. This thing is actually cutting the curve at 2. That's not clear. Maybe I was looking for roots of a quadratic. Then you can just do plot range. So this command here tells you where you should show the output. So now I can see that my quadratic has no zeros, 2 complex roots. You'll learn what that means later. Okay, so no real roots. But maybe we want to understand how a function behaves as we change something. You can plot multiple functions on one curve. X, x squared, x cubed, x to the 4, x to the 10, x to the 20, x to the 100, plotting them all between 0 and 1. And you do this. You also have this line up the top, and we'll talk about that in a moment, but basically it's just saying that it can't evaluate this last one at a certain point because it's just too damn small. Big, small. And you can see x, x squared, x cubed, x to the 4, x to the 5, x to the whatever, lots. And you can start to put these together. These are helpful for papers and other such things because you often need to show data in this way. If you want to store multiple things at once, you can create a table. A table is just a data structure that says, I want a bunch of different items of data in a line. However, Mathematica knows how to plot stuff. So you can feed a table into plot. It'll have a bit of a whinge. It's actually trying to plot everything we did, but it's doing a terrible job of it. And the reason for that is because most of what it's trying to plot is concentrated around 0. And you'll notice I said it picks its range to plot most of what it sees. But what you can do is do the correct plot range. And we also put this quiet at the end to stop it complaining about how small those numbers are. Be nice if I could do that to you guys. Yeah, wow, catty. And yeah, so we can get these nice plots. And it's really good to learn how to do this because this is what will really help you understand things, particularly when we do 3D plots of surfaces. You can get plots are just objects, and you can do them in things like a table. A plot is an object, just like a number, just like a function, which does mean you can do weird things. This is not useful information, but it's fun to see. I can differentiate the plot of x between -1 and 1 with respect to itself. And the answer is 1, because it's just an object, a dummy variable like any other. That's not useful. You should never do that. That is wildly misusing that type of data. But it is a good thing to understand what Mathematica is storing, because what that means is when things go wrong, you know how to fix it. And finally, manipulate. This is fun. You can give a range, and you can vary. So here we are varying n between 1 and 50. And you can see as n increases in x to the n, it gets steeper. This helps you play with variables. A really neat one is this last one here. A few more complicated examples. What we're going to do is we're going to look at how the Taylor series for sine of x converges to its true value. Yeah.
Is manipulate actually calculating every time?
Yes, it's really slow and painful. Calculating it every time. Yeah, it's gross. No, sorry, it calculates them all at the start, I think. I don't remember. So what I've done here is I'm saying let's look at the factorial, the Taylor series polynomial for sine of x. And you'll notice I've done -1 dot. So the reason for that is I'm telling it I want to treat all numbers as decimals, because it will try and recalculate them every single time, and that is incredibly slow. Which is why when you use manipulate, try and be careful not to use exact algebra. Okay, fine, some technical things. What do we see? Well, we see something cool. So this is starting with 3 terms in our Taylor polynomial. 4 terms, 5 terms, 6 terms, 7 terms. The more terms I take, the better an approximation I get. You should know that from first year. Yeah. I know what Taylor series look like. It doesn't tell you. It's an annoying feature. Yeah. So you can count the number of turnovers. All right, we're almost done. Pay attention for a little longer. And this is really nice. If I'd shown this to you in first year, you could have used this to learn the Lagrange remainder formula, which is important and everyone gets wrong. But you can start to see that this manipulate is not just let's make cool pictures, but actually let's explore the theory we're learning a little bit. You may be able to calculate out a Taylor series to 5 or 6 terms, but by seeing it go up to 30 terms, you can really start to see this work. This is going to be really important when we solve partial differential equations later on, because we're going to have a lot of infinite series, and we're going to actually use this kind of process to see what those infinite series are converging to. This is being taught to you for a reason. Okay. There are some more complicated examples at the bottom. It's 10-2. Why not? You can keep going with this. These are, I'm not going to go through these here, but these are on the worksheet. These are essentially problems from the vector calculus review tutorial. I'm trying to remember if I gave you the vector calculus review tutorial. I'll give you a vector calculus review tutorial. These are questions from a tutorial sheet you don't have yet. But it's quite nice. You can do some useful things like differential operators. Here you can see they've used the Laplacian, which actually allows you to calculate more complicated multivariable gradient expressions, and you can start to solve differential equations. You don't need to go through this unless you're really enjoying yourself. As long as you can handle up to manipulate, then you're in pretty good shape at the moment. Play around with this yourself. But the important thing is I want you to use Mathematica to supplement your learning. I don't want you running down blind alleys, you know, spending ages computing something. And to that extent, there's something I want to make abundantly clear, because nobody trusts us when we say this. If you are doing your assignment and you use Mathematica to simplify something, you can just say, I used Mathematica to evaluate this. It is fine. That is Mathematica's job. Your job is to know what to evaluate. Okay? Division of labor is essential to success. We're going to wrap it up there, but as a reminder, in some weeks I will probably have to use a bit of the seminar time for teaching. I will try and keep that minimized. It's only if I feel that we need the space in order for me to explain stuff well. Other than that, get Mathematica on your laptop. Bring it along. Play along with me. It's fun-ish. Yes, hi. Did it not? So I'm not tech support, right? If you can't go through the website I showed you, contact IT. Yeah, I don't know. Every computer's different. Yeah, cool. No worries. Cheers. See you guys. No worries.
How do you write like the normal stuff? Like, you know how there's just full sentences that aren't expressions next to...
Yes, it actually tells you it. Oh, yeah, let me show you. Yeah. No worries.
I was really want to take notes. Okay, this is what this actually does.
Yeah, great question. If you click on that line, you can plain text.
Thank you. That's cool. Have a good day.
Hey. Good question. Yes. Well, space is a better word. We know tangent plane is understood. Tangent space is probably a better word for it. But a plane can be thought of as an n-dimensional object. A plane in n dimensions is essentially an n-1 dimensional space.
Oh, yeah. Okay.
So in 3 dimensions, a plane is exactly what you think it is, and it always carries on just being 1 dimension short. But tangent space is probably a better way to say it. Hello.
I had a few questions. Are you in a rush by any chance?
I mean, I have to clear the room at some point. What are your questions?
Okay. Well, firstly, I know it's a little bit creepy, but I'd like to take a look at what my lecturers do
Yeah,
for
fine. Go
research
for gold.
and for profile and stuff. I was just curious about the Airy function and the Stokes phenomenon.
Yep.
I read a little bit about it because I'm interested in mathematical physics.
Yeah.
So I was just curious. Like, I saw you did some research in January.
Yeah.
I was just curious, like, what kind of contribution.
So the interesting thing about the Airy function,